So far, we have seen the Schrodinger picture. And in the Schrodinger picture, the operators are frozen in time. Say phi is an operator. It had some spatial dependence, but the time dependence was fixed at some point, time t0. And in the Schrodinger picture, the states, they can depend on time as well as space. And their time dependence is governed by the Schrodinger equation. Whereas in the Heisenberg picture, the fields have spatial as well as temporal dependence. So we wrote that as just phi of x. Whereas the states were frozen in time, say at time t equals to t naught. Of course, the Schrodinger picture and the Heisenberg picture are connected by unitary transformation, which means that the physics, that is the expectation values of operators, remain unchanged. For interacting quantum field theories, it turns out there is a third picture which is useful, and it's known as the interaction picture or the Dirac picture. So what is the interaction picture? So let's just start in the Schrodinger picture for an interacting quantum field theory. So we start in the Schrodinger picture for our interacting field theory. And we quantize the fields. This quantization is known as second quantization, which is a misnomer because there was no first quantization. So the quantization is done at some fixed time, so there's no time dependence here. And for the scalar field theories, it's given by something like this. And of course, the commutation relationship between phi's and the commutation relationship between, say, the pi's vanish. So now what we do is that we write the total Hamiltonian in the Schrodinger picture, H, in terms of the free Hamiltonian and the interacting Hamiltonian. And then we go to the Heisenberg picture. So in the Heisenberg picture, if you go there, then the fields become time dependent. But you can see that because the transformation to the Heisenberg picture is through a unitary transformation, this commutation relationship just becomes this one. The other one will still be 0. This just becomes time dependent on the left-hand side. But of course, we are taking the 2 time here to be the same time, so it's an equal time commutation relationship. On the right-hand side, the unitary transformations just cancel each other, and therefore we don't have any time dependence on the right-hand side. So this is the commutation relationship in the Heisenberg picture for interacting quantum field theories. So let me just make it clear. Phi of x of t is equal to, well, we can write this as phi of x, and that's equal to e to the power I h of t phi at, well, this was not dependent. This didn't depend on time, so it was only dependent on x and e to the power minus I h t. Similarly for pi. So at a fixed time, we can expand the Schrodinger field operator. So this is at a fixed time. So let's just take that time to be t0. And that will have, we can always expand this as a Fourier series. So in the Schrodinger representation, we see that on the right-hand side, there is no time dependence. That is appropriate for the Schrodinger picture. In the Heisenberg picture, of course, the field operator is defined as we saw below. Here we are introducing t0 because we are not choosing the Schrodinger operator to be at some zero time, but at an arbitrary time t0. Now, in the interacting quantum field theory, the Hamiltonian is no longer a quadratic Hamiltonian. And therefore, the expression for the Heisenberg operator for any arbitrary time, starting from the expression of the Schrodinger operator at t0 given by here, will not in general be of a form which is what we assumed, what we found for the Heisenberg operators in a free field theory. Because if you remember, if the Hamiltonian H was the free Hamiltonian, then we could derive from this thing and this expression and the commutation relationship an expression for phi of x as a Fourier series like this, except over here there was a four-dimensional vector product, and over here there's a four-dimensional vector product. But because H in an interacting theory is no longer quadratic, starting from this, we are not assured that phi of x will have that identical expression. Let me just remind you what phi of x is for a free theory. So for free theory, so for free theories, that is where the Hamiltonian is just the quadratic part of the Hamiltonian, we show that phi of x, the Heisenberg operator, for any time is given by a of k e to the power minus I kx. Here it's a four-dimensional dot product, and then a dagger of k e to the power plus I kx. But what I'm saying is that if the Hamiltonian is not the free Hamiltonian, then this expression starting from this guy will not give you this. Okay, so let's keep that in mind. And one of the reasons for introducing this new picture is so that we can get an expression for the wave operator, which is familiar to, which is similar to this expression. So in the Heisenberg picture we just saw, it's worth repeating, the field operator is given by exponential of I, h, t minus t0, phi of x at t0, e to the power minus I, h, t minus t0, and where this h is a full Hamiltonian. Now, if I define some operator, which I call phi of I of x, where I stands for interaction picture, where we start with the Schrodinger picture operator, but instead of doing a unitary transformation with the full Hamiltonian, we just do a unitary transformation with the free part of the Hamiltonian. So if you do this, because the free part of the Hamiltonian is quadratic, and therefore, by the commutation relationship, it'll give us an expression for phi of I at any time x, space and time x, an expression which matches the expression for the free field theory in the Heisenberg picture. So this is a remarkable fact, and this is one of the reasons why we go to the interaction picture. Note that if I take the interaction picture field, that is equal to the Heisenberg picture field, but in the limit where the interaction term goes to 0. So lambda is some parameter which parameterizes the strength of the interaction. And if you set it to 0, then our Heisenberg operator becomes our interaction picture operator. So starting from this expression, here the left-hand side, we have the interaction picture operator. And on the right-hand side, we have this is the Schrodinger picture operator. We can, of course, relate the interaction picture operator to the Heisenberg picture operator. And we can just write phi of I of x. And we have e to the power I h naught t minus t0. And now in this expression, we just replace this by its relationship to the Heisenberg picture operator, which is going to be given by e to the power minus I, the full Hamiltonian h, then t minus t0, phi of x. So this is the Heisenberg picture operator. And then we have e to the power plus I, full Hamiltonian h, t minus t0 times e to the power minus I, h naught t minus t0. So this is the relationship between the Heisenberg operator and the interaction picture operator. We can invert this relationship and we can write phi of x, the Heisenberg picture operator, as e to the power I h t minus t0 e to the power minus I h naught t minus t0 phi I of x e to the power plus I h naught t minus t0 e to the power minus I h t minus t0. So we can also express this as phi of x is equal to, we can call this a unitary operator u, and it depends on so this is u dagger, and it depends on t and t0. And then here we have phi I of x. And here this is the definition of what u is. It also depends on t and t0. So the operator u of t to t0 is the time evolution operator in the interaction picture. It's the time evolution operator in the interaction picture. And the reason why that is so is because if I take the interaction picture state, which is defined by u of t comma t0 acting on psi at t0.